Okay, perfect. So welcome everyone to another MCRN Colloquium, and thanks, Matt, for agreeing to give a talk on short notice. Really appreciate it. I'm looking forward to it. Um, just a little bit about Matt. He's at George Mason University. His research interests are in differential equations, existence and stability of traveling waves, dynamics on complex networks, and pattern formation. Before he was at Mason, he got his PhD at Boston University, and he did a postdoc at University of Minnesota, all places where MCRN has its fingers in, I think.
Mhm.
Um, so that's always great to see. And today, Matt's going to talk to us about robustness of pushed and pulled invasion fronts in singularly perturbed reaction diffusion systems. I'm excited because I see reaction diffusions everywhere. So this should be
Okay,
interesting with Matt. Yeah, let's take it away. Thank you.
awesome. Thank you very much for the invitation and thank you for the introduction. So yeah, today's talk is going to be a little less climate focused, but I suppose if you showed up today, you knew that already. So I'm going to be talking about kind of traveling waves in systems of reaction diffusion equations, in particular waves or traveling fronts that propagate into unstable states. So this will be joint work with Montie Avery, who's at Boston University, and Arnd Scheel from the University of Minnesota. In terms of an outline, I want to, kind of spend about half the talk probably giving you a little bit of background, telling you about kind of fronts that propagate into unstable states and some of the kind of the unique characteristics that that kind of describe them. And then I'll spend probably the second half of the talk talking about kind of a research project that was joint with Monty and Arnd, about some persistent results for singularly perturbed systems of reaction diffusion equations. Okay. So just to kind of give you the general setting, right? So we're thinking about having a system or you won't see a system for a while, but so a reaction diffusion equation with an unstable homogeneous state. Okay. So you think about this unstable state being perturbed locally in space. So the perturbation is going to grow because of the instability. It's going to spread because of the diffusion. And what you expect to eventually see is kind of a pair of counterpropagating fronts moving out from where the instability was initiated. Okay. So with these fronts, you really care about two principal things, right? So first of all is their speed. You could think about this in kind of say applications to kind of epidemics, right? Where you have this say epidemic that's propagating spatially, right? So if you know how far you are away from the front, and you know the speed at which the front is moving, you know basically how long you have to kind of prepare for that front to arrive where you are. Okay. You could also imagine situations where you have this instability, it grows and it spreads, and it's going to select some other state, right? So you can imagine there's a lot of different kind of, say, stable or metastable states out there, and you want to understand kind of where the system's going to transition to next. And oftentimes this is kind of mediated by these traveling fronts, and so if you understand the traveling front, you understand basically what happens next in the system, okay? So, kind of like I said earlier, we won't get to systems until later in the talk, right? But there's a lot of tools that you can use for kind of scalar reaction diffusion systems that don't necessarily apply for systems of equations. Just keep that in mind when I'm kind of giving you examples of scalar PDEs in the beginning, first half of the talk. And really, I think kind of the main thing that I want to kind of convey to you, especially in the background section of this talk, is kind of there's two different mechanisms for kind of front propagation when you're propagating into unstable states. And these are kind of called pushed and pulled fronts. So if nothing else, hopefully you come out of this talk with an understanding of kind of what's a pushed front, what's a pulled front, what are the characteristics, and kind of what are you kind of looking for when you identify these fronts in a problem. Okay. After that, I'll kind of move to the research portion of the talk. This is, again, kind of like a persistence result, right? So you have a traveling front for a specific system and a specific parameter. You want to change parameters, and you want to kind of understand what effect that has on the front and its stability, okay? So I'll kind of do a little bit of background there, talk about kind of an example where things are weird in systems, and then I'll get to kind of the main crux of the research, okay? So I want to start kind of very simple. So this is going to be a situation of a scalar reaction diffusion system up there. You have a stable state at u is equal to 1, you have a stable state at u is equal to -a, and you have an unstable state at u is equal to 0. Okay, so you want to think about, okay, so if A is less than 1, you think about the ODE part of this reaction diffusion system as having an energy. So you have kind of these three steady states, which are the minimum or local minimum or maximum of the energy. And you want to ask yourself, okay, so if we start with, say, some sort of initial condition for our PDE, which looks like this stable state 1 on the left, looks like the stable state minus A on the right, you want to understand kind of what's going to happen, okay? Keeping in mind that these are both stable states for the OD, right? So, locally over here, the system's happy because it's near a stable state. Locally over here, the system's happy because it's near a stable state. And the kind of issue is this kind of interface here, where you have this diffusive term that now is going to want to kind of smooth this out. And what's going to happen is you're going to end up seeing the formation of a traveling front, and this interface is going to move one way or another, okay? So the question is basically like what determines which direction the interface moves and what is the speed at which it moves, okay? And this is a simple example so you can answer that kind of explicitly. And so if you simulate this thing, what you notice is that it starts to propagate from the left to the right. So this corresponds to basically an invasion of the stable state minus A by this other stable state 1, okay? And the reason why in this example, right, the reason why the state at 1 wins is because it has a lower energy for the nonlinear ODE, okay? So on a nonlinear level, the system prefers the state U is equal to 1 to U is equal to minus A. And so you see the front propagating in the direction of the higher energy state. So again, you can kind of work out, this is a special example, so you can work out kind of exactly what the speed is in this case. And you see that it is exactly proportional to the energy difference between these two states, okay? So again, there's this kind of nonlinear mechanism that determines the direction and speed of the front in this bistable case, okay? So now you can play the same game, but replace the stable state minus A with the unstable state 0, right? So you've got 1 on the left, you got 0 on the right, and you're going to play the same game, basically. So you already know that because this is an unstable state, right, it's going to have a higher energy than the state at 1, right? So you expect that on a nonlinear level, the system's going to prefer the state at 1 to the unstable state at 0, and that's exactly what happens. But there's also kind of a second thing at play here, which is that 0 is an unstable steady state of the ODE, okay? So in addition to kind of having a nonlinear preference for the stable state at 1, there's also this situation that, if you perturb an unstable state, your perturbation is going to grow and it's going to spread. And so there's a second kind of mechanism that can lead to your spreading of fronts in this case, okay? And so if you think about, okay, so the different mechanism is the fact that this state at 0 is unstable. Let's linearize about the 0 state, and let's ask basically how fast things move in the linearized system. So there's more complicated ways to do this, but let's just do it in the most simple way, which is like you linearize at 0 and you look for solutions, okay? So the simplest solution that we know of this is basically the heat kernel, right? So if you solve this using the heat kernel, you get kind of your heat kernel type term, and then there's this pointwise exponential growth coming from the instability of the 0 state that kind of goes along with it, right? So you have this kind of heat kernel, which is spreading out kind of slowly, and it's also kind of being, there's this pointwise exponential term as well, okay? So if you want to compute the spreading speed in this situation, you're really just asking, like, how fast does an observer have to move in space so that you keep pace with the instability, right? So, if you go too fast, you'll look like the solution's decaying exponentially. If you go too slow, it'll look like the solution's growing exponentially. And the spreading speed is kind of that exact rate at which you're kind of in between these two things, okay? So you plug that in, and you can kind of see, well, C is equal to 2 times the square root of A is going to be the spreading speed for this equation, okay? So in this case, now I'm making a leap here, right? So if you look at kind of the spreading speed for the fully nonlinear PDE, you see that there's parameter regimes where you have one of two different behaviors, right? So if A is less than a half, you end up with the spreading speed of 0 invading 1, again being kind of nonlinearly determined, right? So there's a nonlinear preference for the state at 0, sorry, the state at 1 as opposed to the state at 0. And so you see a spreading speed that's proportional to this energy difference, okay? But on the other hand, if A is bigger than 1/2, then what you end up seeing is just always fronts propagating with the exact same speed as the spreading speed of the linearization, okay? So you have these two different mechanisms, and that will be kind of the basis of what I'm going to talk about next. Okay, yeah. So if you fix basically A is equal to 1, now you're in this regime, right, where you expect to just see the linear spreading speed. And so if you haven't seen this before, I think it's kind of remarkable, right, that you have this kind of solution, which is here, which is a traveling front solution, right? It's far from equilibrium, right? It's not a near equilibrium solution, but still there's something about this linearization which we kind of intuitively expect to only be valid near the unstable state. But there's this feature of the linearization that is kind of playing an important role in this far from equilibrium solution. So if I just evolve kind of these things with nearly identical initial data, right? So blue is going to be the front, red's going to be the linearization. What you'll see is they stay very close to one another, right? So, the red thing, it's growing exponentially in time, right? So I'm cutting it off and only showing you basically where it intersects the interval from 0 to 1. But what you notice, right, is that like the linearized solution is keeping pace with the nonlinear solution. Maybe I should say that backwards, right? The nonlinear solution is keeping pace with the linear solution. Okay. So, okay, good. So I want to kind of talk a little bit now about kind of fronts, right? So what we've seen in simulations and what we expect is the formation of this traveling front. So let's go out and find it, right? So again, kind of restricting to this simple case where A is equal to 1 in my original example. This is known as the Fisher-KPP equation. You can look for traveling wave solutions to this equation, right? So you look at this in a co-moving frame with speed c. You write it as a system of first-order equations. And then you're going to look for heteroclinic orbits or heteroclinic connections between this state 1, 0 and this state 0, 0. Okay. So now what's kind of interesting when you have fronts propagating into an unstable state is, because of the fact that you have this unstable state, so this has a negative sign here. So if you think about what the eigenvalues are at the origin, right, you have trace determinant plane. So the trace is always negative. The determinant is always positive, right? So you know that you have two eigenvalues that have the same sign, and because the trace is negative, they both have negative signs, right? So the point is you have basically a two-dimensional stable manifold here, whereas over here you have a one-dimensional unstable manifold, okay? So what that means is like you're intersecting a two-dimensional manifold and a one-dimensional manifold in two-dimensional space. This is a robust intersection, okay? So for every positive wave speed, you expect to see a traveling front solution, okay? Now the characteristics of these fronts depend a little bit on the speeds, okay? So there's really kind of three qualitatively different regimes here. So if C is bigger than 2, your linearization at the origin has two stable eigenvalues, real eigenvalues, okay? And you can do like a trapping region argument to show that this heteroclinic is always going to come into the origin along the weaker of these two eigendirections, right? So with the weakest possible decay. On the flip side, right, if you make C less than 2, now your eigenvalues at the origin are complex conjugate. So you expect oscillations in your solution, and you see the existence of a front that's non-monotonic, but approaching the origin, okay? And exactly in the middle, you have this kind of front that has speed 2, and this corresponds to a Jordan block in the linearization, a repeated eigenvalue in the linearization at the origin, okay? So for every speed, you get a traveling front, and the question is basically like, which of these do you care about, okay? And so what I'm going to try to argue is that what you care about is kind of the stability of these fronts, okay? So you want these fronts to have certain stability properties that are consistent with being selected by localized initial data, okay? So if you're familiar with kind of Sturm-Liouville theory, right, this is a scalar reaction-diffusion equation. So any front that oscillates is necessarily going to be unstable, okay? So we can kind of eliminate these oscillatory fronts from our kind of possible selected fronts almost immediately, okay? It'll turn out that this front with speed 2 is the front that we see, but it's a little bit more subtle to kind of understand why that front is preferred over or selected over the other fronts, okay? So in order to kind of study the selection, right, you have to think about stability, okay? So another aspect of the fact that these are fronts propagating into unstable states is that if you look at the system in, say, L2, they're always unstable, right? So you have this front, it's invading an unstable state. You put a perturbation out by the unstable state, that perturbation is going to grow, right? They're unstable fronts, okay? And so the way that you have to kind of, so why would you expect to see these unstable fronts in practice, right? So you can imagine a situation where you have this traveling front interface, and if you make a perturbation like right next to the interface, you can imagine basically the interface, the front kind of catching that perturbation and absorbing it, and then kind of being stable in that way, okay? And that's exactly what happens, right? But what it means is that, if it's stable with respect to a perturbation that you make right near the front interface, in order to make a perturbation way ahead of the front interface, it's going to have to be much smaller than the perturbation that you make right ahead of the front interface, okay? It's all very kind of informal, right? But that's kind of the idea, right? So what that means is that you need some way to kind of measure the size of your allowable perturbations as a function of the distance from the front interface, okay? And so typically what you do is you look at this in exponentially weighted spaces, okay? So when you look at it in exponentially weighted spaces, like I'm going to focus on these two cases here where you have this critical case where you have c is equal to 2. You have this supercritical case where c is faster than 2. So remember that these fronts that we constructed, or we looked at in the previous slide, right? And in the case c is greater than 2, these all have weak exponential decay, okay? And so what that means is that if you look at these in an exponentially weighted space, you can kind of push the essential spectrum all the way over into the left side of the complex plane. But in doing that, you eliminate the translational eigenvalue that you might expect to exist for the system. Okay, so the exponential weight that you look in removes this translational eigenvalue. Okay. On the flip side, when you look at the critical front, what you notice, or I guess I'm not showing you this, but if you look at kind of the essential spectrum in exponentially weighted spaces, you can move this essential spectrum all the way to the negative half of the imaginary, the negative real axis, but it always comes all the way up to the origin. Okay, so there's always kind of essential spectrum that touches the imaginary axis for these types of fronts. Okay, so. Good. So this is kind of the one possible scenario, right? So you have these kind of unstable fronts. You have these fronts that are too stable in a sense, right? Because they lose this translational eigenvalue. They can't attract kind of localized initial data. And then you've got this front that sits in between, and this happens to be the selected front in this case, okay? Now, let's think about kind of a different type of, or different value of A, right? So if I make A much smaller, now I'm kind of in this regime where the speed is going to be nonlinear selected. And I want to kind of think about kind of what are the traveling fronts in this setting, right? So now I'm going to look at these as a speed, as a function of the speed, right? So I'm constructing heteroclinic orbits as a function of the speed. If I start fast, like at speed 2, what you see is you see this heteroclinic connection, and it comes in and it goes in, as in the last case, along this weak stable direction, okay? I have a movie, but maybe I'll just kind of advance it piece by piece if I can. That's not really working, is it? Okay. Okay, so if I advance it, if I decrease the speed just a little bit, right, what you notice is that you still are coming in along this weak stable direction. You decrease the speed more, same, until eventually you find a parameter value, a speed value, where this heteroclinic comes in along not the weak stable direction, but the strong stable direction, okay? And then if you make the speed any smaller, right, now you end up kind of going through this strong stable manifold and you approach the origin along the opposite direction, right? So you now have a non-monotonic front. And again, these fronts are not going to be stable, okay? So the point is here that the selected front is not going to be the one that propagates with the linear spreading speed, but it's going to be propagating with some faster spreading speed corresponding to the unique heteroclinic connection that connects 1, 0 to 0, 0 along the strong stable manifold or strong stable eigenspace. Okay. So, okay, so this is kind of what's known as a pushed front. The idea of a pushed front is that, well, basically the front is being propagated by a nonlinear mechanism that really kind of lives behind the front interface. The previous example I talked about, this is what's known as a pulled front, right? And this is really being driven by kind of the instability ahead of the front interface. Okay, so these are these two different types of regimes of fronts that you can see in this context. Okay. I'll mention just briefly, right? So, I said when A is bigger than a half, you have pulled fronts. When A is less than a half, you have pushed fronts. And so you might ask, well, what happens at the transition point? So if you're exactly at A is equal to a half, again, if you look at this in a frame with the linear spreading speed, you have this Jordan block at the origin. You still have this kind of heteroclinic connection. The difference is that, well, in this case, again, it's special, so you can actually write down the solution explicitly. But what you see is that kind of your solution has strong exponential decay in the sense that this kind of generic algebraic prefactor that you expect for solutions near a Jordan block is missing, right? So you're kind of on the boundary between these two things here. Okay. So just to kind of recap what we talked about, right? So there's pulled fronts and there's pushed fronts. Pulled fronts are kind of special in the sense that the invasion speed that you see in the nonlinear system is exactly equal to the spreading speed that you see in the system linearized about the unstable state. Okay. Generically, these things, if you look at the decay rate far ahead of the front interface, they have this Jordan block structure, right? So generically, they have this kind of algebraic prefactor. Generically, they're marginally stable in the sense that you can come up with an exponentially weighted function space that pushes the essential spectrum to the negative real line, but you can't do any better than that, right? So you always kind of have essential spectrum touching the imaginary axis. And then there's a couple other kind of technical things that won't be super relevant to what we're talking about today, but there's not an embedded translational eigenvalue. And then there's kind of some convergence results in terms of kind of how quickly you expect your solution to converge to these front profiles. Okay, but again, the main idea is that for pulled fronts, the nonlinear spreading speed is the same as the linear spreading speed, and the stability and they're marginally stable with continuous spectrum touching the imaginary axis. Okay. For push fronts, right, the speed is really determined by a nonlinear effect, okay? And this means that you typically have an invasion speed that's larger than the linear spreading speed. To identify it, you really need to do kind of like a traveling wave analysis, right? So you need to look at heteroclinic orbits. You need to try to find the special heteroclinic orbit, which has strong exponential decay, okay? The reason why you care about this strong exponential decay is really a stability result, right? Because when you look at the spectrum in an exponentially weighted function space that stabilizes the essential spectrum, you want this kind of translational eigenvalue to still be there. And again, this is because you want it to be kind of selected or be able to be selected by localized or compactly supported initial conditions, right? So, good. Okay, so that's the background. That's pushed fronts, that's pulled fronts. And so now I want to kind of move on to the second part of the talk here. Well, I guess I'll move on in a second, right? But so what I should say before is that this is a very old and well-studied problem, right? So kind of there's really fundamental results on the Fisher KPP equation that date to the 1930s, okay? And there's been just really a lot of kind of work in the last almost 100 years on these types of problems, okay? So in the interest of time, I'm not going to go through and give everybody the credit that they deserve, but I do have some names listed here, and I'd be happy to kind of point people in directions later. And there's all sorts of names that should be on this slide and are not, right? So, okay. So, in the second part of the talk, I want to talk about kind of the research project, right? So, again, we're kind of interested in fronts propagating in unstable states. We're thinking about kind of systems of reaction diffusion equations, right? And so kind of, the thing that's nice about scalar equations is that there's a lot of tools that you can use for those equations, right? So, you think about kind of the traveling wave equations that I drew for you earlier, right? These are planar ODEs. You have some hope of kind of analyzing those types of things, right? So if you look at a system of reaction diffusion equations, now your traveling wave equation lives in four-dimensional space, and it is a lot harder to kind of draw pictures and construct trapping regions and try to understand kind of what happens to these traveling waves, okay? Other types of tools that you have for scalar reaction diffusion equations also either don't necessarily translate to the systems case, or if they do, they're much more difficult to apply, right? So for scalar equations, you have comparison principles. Oftentimes you don't have those in systems. There's a lot of kind of really interesting kind of variational results that you can apply to scalar equations. Oftentimes they don't translate to systems, right? There's kind of probabilistic ways of viewing these front propagation problems. These oftentimes don't translate to systems, or if they do, they are much harder to apply, okay? So if you have a system of equations, then what are you supposed to do, right? And so, kind of one possible avenue for analysis is to say, okay, we have a system of equations. There's some parameter in the system. We're going to take that parameter, we're going to make it asymptotically small, we're going to make it asymptotically large. And in that limit, we're going to try to hopefully obtain a reduction to maybe something that looks like a scalar reaction diffusion equation where we can kind of take these tools and apply them. So the main example that we're going to be talking about is kind of a logistic Keller-Segel type model. I'll motivate it later when we kind of go back and talk about it for real. But I just wanted to kind of like do some really kind of simple kind of analysis here and explain kind of what the idea that I was just talking about, right? So we've got a system of reaction diffusion equations. We got a parameter delta. Let's assume this parameter is small. So in fact, let's just make it 0, right? So if you make delta 0, this second derivative term drops out. And then what you see is kind of formally u has to equal v, okay? So if u has to equal v, you can go back into the first equation and substitute one for the other. And what you obtain is exactly a scalar reaction diffusion equation, okay? So if you can find kind of traveling waves and traveling fronts in this kind of reduced scalar equation, the question is basically, can you kind of, take those fronts and do they kind of survive basically when you look at them back in the full system, okay? And so that's really what this talk is about today. And I'd say that, the math that we're doing is in this kind of specific context, right? But I'd like to say that this, the ideas that we're developing here kind of do apply kind of more broadly. And so, yeah, okay. So, what are we going to do? Kind of what is the math about, right? And so the idea is basically we're going to take some kind of regular perturbation results. And I should say this isn't my work. This is work of Montie and Arnd's. And we're going to combine those with some singular perturbation theory to kind of, take these kind of reductions and then bring them back to the full system, both in terms of their existence and their stability analysis. Okay. Okay. This is where I get a little embarrassed, as I was saying earlier, right? So we're going to start, and I just want to walk through kind of regular perturbation results for scalar reaction diffusion equations, starting with bistable, the bistable regime, okay? So here's my beautiful picture that I made like half an hour ago. So normally I'd have a whiteboard and I'd be drawing, but this is what I have to do today. So, okay, so let's think about just a bistable case, right? So in the bistable case, you have kind of like a steady state. When you look at it in the traveling wave equation, it becomes a saddle with a 1-1 splitting. You have another stable state here at 0, and it also becomes a saddle with a 1-1 splitting, okay? And so what we know is we have this kind of heteroclinic orbit that connects these two fixed points. They both are intersections of one-dimensional manifolds. This is not structurally stable, right? So if we change our parameter c, or sorry, if we change our parameter delta, we expect generically this heteroclinic connection to break, okay? And this is not new, right? People have studied this for a really long time. And the idea is that basically when this heteroclinic connection breaks, what you need to do is you need to repair it, and you need a parameter to repair it. And so the wave speed ends up being a parameter, okay? But the idea is that you want to kind of patch this up by changing kind of another parameter in your system, in this case, the wave speed, okay? So again, there's plenty of ways that you can do this. You can do this with a phase plane analysis. You can do it with Melnikov integral type methods. So nothing that we're doing here is kind of new, but it's going to kind of translate over to the pushed and the pulled case, I think, a little cleaner than the methods that are already developed here. And so anyways, so what you want to do is you're trying to find a traveling front solution, right? And so you think about, okay, well, I want a solution to my PDE, right? And these solutions, right, the heteroclinic is unique, but as a solution to the PDE, there's a bunch of translates, right? So you need some sort of phase condition that fixes the translate of the wave that you're looking at, right? So now you have this kind of operator, right? You want to think about this as an operator on some nice function space, so like H2 to L2, okay? The problem is like this front, right? Because it connects 1 to 0, it's not in L2, okay? So you need to kind of localize the problem. So write Q as basically some cutoff function near the state at 1, plus some localized function W that's in L2, okay? So I'll write, it's kind of ugly if you write all this stuff out in terms of W, so I'm just going to leave it in terms of Q, but Q is chi minus plus this cutoff function plus W, okay? And so now what you want to do is you want to apply the implicit function theorem, right? So we know that if we start at delta is equal to 0, there's a speed and there's a front for the system. That's kind of the standing assumption, okay? And now you want to perturb this. And so what you do is you try to apply the implicit function theorem. So you look at the joint linearization in W and in C, okay? You get this kind of type of linearization here. So this is just the linearization about the front, and this is kind of the corresponding linearization for the phase equation, okay? And the implicit function theorem says that as so long as this doesn't have a kernel, or that this is boundary invertible, then you can continue the solution, okay? So the key point is that this linearization is Fredholm with index 0, and it has a trivial kernel, so you can invert it, okay? And you can apply the implicit function theorem, and solutions persist for sufficiently small delta, okay? The key reason why this has no kernel, right, is you think about this kind of linearization about the front. It has a kernel element, which is the translation, is the derivative of the front profile, which is the translational eigenfunction. But you've effectively kind of removed that by imposing this phase condition, okay? So linearization is Fredholm index 0. It's got a trivial kernel, so you can continue these things. And one thing that's nice about the implicit function theorem is that you can just kind of, you can compute expansions very easily, right? So natural thing is like you perturb this thing in delta, you want to know, does the speed go up, does the speed go down? And this gives you at least a formula by which to kind of answer that question, right? You may not be able to actually compute it given how complicated these things are, but it gives you a formula by which to kind of do this, okay? So this is the bistable case, right? Again, there's nothing new here. This is, things that have been done before. Let's talk about the pushed case, right? So here I've got my picture again, right? So now in the pushed case, the zero state is unstable. So when you look at it in the traveling wave equation, you get two stable eigenvalues, okay? One weak, one strong. But we're in the pushed case, right? So we're always coming in along the strong, stable direction, okay? So again, you're going to kind of set this up in this way again, and you're going to try to repeat what we did in the bistable case, okay? So the issue, though, is that when you kind of look at the linearization, it ends up being a Fredholm operator, but it has a positive index, right? Which means it has a kernel, but no co-kernel, no matching co-kernel, okay? So the reason for that is that, it has a higher dimensional kernel than it does co-kernel. So if you look at the linearization about the traveling wave, again, this thing has a translational eigenfunction, okay? But if you look at kind of the corresponding thing that should be in the co-kernel, it's this exponentially growing term times the translational eigenfunction, okay? And the issue is that, because of the way this works out, this ends up not being an L2 function, okay? So what's going on here? Well, what's going on here, right, is that you already know that you're not exactly in the same regime as in the bistable case, right? So if I perturb this, right, and I think about, okay, does my solution persist as a function in L2? It always does, right? Because you have kind of two stable directions here. So no matter how you perturb this, you're gonna break the strong stable connection, but you're still gonna have a traveling front that connects these two states, okay? So you somehow need to kind of adjust your problem so that you're really looking for something that stays in this strong stable manifold, okay? So to do that, you work in an exponentially weighted space, just like I kind of talked about earlier. And there, when you do that, right, you can find a weight where the translational eigenfunction stays in the space, okay? But you get enough kind of decay in your exponential weight so that the co-kernel also remains an element of L2, of the space, or the weighted space, sorry. And so when you do this, then everything becomes completely analogous to the bistable case, and you can apply the implicit function theorem. You get the persistence of these fronts, and you can do kind of stability in kind of standard ways. Okay, so in particular, by Sturm-Liouville, you know this thing's going to be monotone, and so you know it will be stable as well. Okay.
I have a question, Matt.
Yeah.
So if you go back to one slide before that.
Yeah.
So when you add, so before the phase condition that you add here, right? So it seems like you're doing a parameter continuation, like some kind of some continuation in for C, right? Because I mean, this looked like that. I mean, is that
Yeah,
what you're doing for that?
exactly, right? I mean, if you want to think about it in that way, right? Like you have basically a one parameter family of fronts, right? And the kind of, I guess, I don't know if this is the right way to say it, but kind of the tangent vector along this direction is given by the derivative of the front profile, right? So if you look at this front minus that front, which are spatial translates, right? That's going to be the derivative of the front to leading order times whatever your translate difference is. Does that make sense?
Right. But my question is like this is in C. So this is for a fixed delta then?
This is for a fixed delta, yeah?
Okay.
And
And
so
all
what this condition says is that like you don't want to look along this family of translates, you want to look basically orthogonal to it, or transverse to it, I should say.
okay. But so another question that I had is if you look at your two-dimensional system, so now you're looking at the scalar equation. Is that correct? Because
Which two-dimensional
so
system?
like the Keller-Segel. I mean, so
Okay, yeah.
so now, I mean, are you assuming U equals V here or because
Okay,
delta?
so this is just we're only doing preparation here, right? So we're in a scalar reaction diffusion equation.
Okay.
I haven't told you anything about it except that we're assuming we have a front when delta is equal to 0. Okay.
Okay.
And
Okay.
later, when we look at this Keller-Segel model, we'll reduce it down to the scalar case.
Okay. And then you'll
Okay.
get some similar results based on this example.
Exactly. Yeah.
Okay. All right.
Okay.
Thank you.
Yeah. Okay. So the push case was basically analogous to the bistable case as soon as we look at work in an exponentially weighted space. The pulled case is different, right? So in the pulled case right now at the origin, you have this Jordan block. Okay. So again, you have like a one-dimensional unstable and intersecting a two-dimensional stable manifold. Okay, you perturb it, you expect that to persist. Okay, but the issue is that when you perturb it, you also might break this Jordan block. Okay, so you might break it in such a way that you end up in this oscillatory regime, and you know your front's not stable. You might break it in such a way that you end up in this kind of regime where you have two unique eigenvalues, and your front will be have weak decay and not be selected, right? So really what you want to do is you want to kind of think about this and perturb it in such a way that you're always keeping this Jordan block structure, okay? And what that means is that you don't get freedom over choosing your speed anymore, right? Your speed is kind of determined so that the linearization at the origin has this Jordan block, okay? And then when you do that, right, you're always going to have a solution, right? Because you, again, have this one-dimensional unstable manifold meeting this two-dimensional stable manifold. But what's important is that it remains stable, okay? And for scalar equations, what that means is that it retains monotonicity, okay? So we have this pulled front when delta is equal to 0. It has this kind of decay rate with this kind of generic algebraic prefactor on the exponential decay rate. As I said earlier, like the speed is no longer a free parameter, so we have to fix it as a function of delta so that we retain this Jordan block, okay? And then if we look at this linearization, we want to kind of play the same game as before, right? So like if we don't impose any decay, if we don't look in an exponentially weighted space with any decay, we're Fredholm with positive index because we have a kernel and we have no co-kernel, okay? The problem here now is that, well, if we look at a decay rate which is exactly equal to the front, we completely lose the fact that this is a Fredholm operator, right? Because our asymptotic eigenvalues become complex or become 0, right? So it's not Fredholm. And if we make too much decay, if we require too much decay, well, we lose our kernel and we pick up a co-kernel, right? So we actually jump from being Fredholm index 1 to being Fredholm index -1, okay? So the idea, and to be clear, like this is Montie and Arnd's work, this isn't my work, right? But the idea is to basically come up to change your ansatz, right? So before we said, okay, we're going to localize our problem by kind of thinking about this cutoff function on the negative half line and this kind of core function, which is more localized. Now, what they're going to do is they're going to build in kind of exactly these two terms that are making this Fredholm index jump from 1 to -1, okay? Which are precisely these two kind of linear solutions that you know, leave the space as you increase the exponential weight through this critical value of nu naught, okay? So you have this kind of more localized core function, and then you've got these two things built in. And it turns out that when you do kind of the joint linearization in W, A, and B, You get a Fredholm index 0 operator. It's got a trivial kernel, and so you can kind of do the implicit function theorem again. Okay. The key point, right, is that like, okay, you get existence, but we got existence for free, right? One-dimensional intersect two-dimensional, right? We could have just stopped there, right? The key point, right, is we want this thing to be stable, and stable in the scalar case means monotone, okay? And monotonicity of the front really means like monotonicity is near the zero state, which means this A naught has to be positive, or have a sign, I guess, but positive, right? And so what you can do is you can kind of apply the implicit function theorem. You get A as a function of delta, and in particular, this is a continuous thing, right? So if A is positive when delta is equal to 0, it's going to remain positive when delta is non-zero, and you're going to retain monotonicity of your front, okay? So that's the key idea. Okay, so now we're down to, oh, I got to tell you about this first. Okay, so now we're going to go to systems. Okay, so we've talked about scalars. Scalar equations, we're going to go to systems. And so I want to just kind of briefly give you this kind of example that tells you that when you go to systems, things can be kind of strange, okay? So we have kind of this Fisher KPP type equation here for U, and it's coupled to this just linear heat equation for V, okay? So V is very simple to understand. It diffuses in space. It decays pointwise with exponential rate of at least e to the minus t over 4, okay? Now, the V component is going to be coupled into the U component through this linear coupling, okay? So what's going to happen? V is going to go to 0, and there's, you can think about U when there's no coupling, when delta is equal to 0, that's just going to form a traveling front with speed 2, and you can think about V with positive coupling, but smaller, not so big, right? And what you kind of expect is that in both cases, right, because V is going to 0, eventually, like, you should just see these two fronts moving, right? So maybe there's some sort of initial transient where it affects things, but then eventually they should just move with the same speed. And interestingly, what happens is not at all the same, right? So you have this kind of U component, this V component, sorry, which is going to 0 pointwise exponentially fast. But the coupled equation always moves faster than the uncoupled one does, okay? And so what's going on here is basically the following fact, right? Which is that when delta is positive, the front is no longer the front that you get in the 0 when delta is equal to 0. It's no longer stable, okay? The reason for that instability is because, well, you have to look at this to study the stability problem. You have to look at this in an exponentially weighted space, and the exponential weight that you need to stabilize the U component without coupling ends up destabilizing the V component, okay? So it's kind of an interesting example, but from the point of view here, right, what that means is like when you go to systems, you lose, in general, you lose Sturm-Liouville, right? So it's no longer the case that just because you have a monotonic front, right, the existence of a monotonic front does not imply anything about stability, right? So we really have to consider stability when we talk about systems, okay? Okay. So this brings me to the system that I wanted to talk about. So this is a Keller-Segel model. So this comes from kind of problems in bacterial chemotaxis. So you think about U as being kind of the concentration or density of a bacteria. This bacteria secretes a chemical V, okay, which has density V. And so you can kind of understand the dynamics in the following way, right? So V is the chemical. And so it has, basically, it's created by U. It degrades at some rate, and it diffuses, okay? So you have kind of normalized these parameters in such a way that you get just U minus V here, okay? Now, the U component is really just a Fisher KPP type equation, but there's also this kind of chemotaxis term, okay? And so you can think about this as basically a flux term that, depending on the sign of chi, is going to push this bacterial to kind of, it's a flux term that's going to push things either up the bacterial gradient or down the bacterial gradient, okay? So the case when chi is negative, this is called the chemoattractive case, right? This is going to be a flux term that's going to push that bacteria up the gradient. When chi is positive, this is the chemorepulsive case, and it's going to push things down the gradient. So in the interest of time, I'll just kind of say that we're going to be focusing on the chemoattractive case, and we were interested in this by because of a paper by Griette, Henderson, and Terranova, okay? So we recover this kind of system of PDEs that I talked about earlier. We're thinking about delta here as being a small parameter. And we want to understand basically what happens in the system when delta is small. Okay. So we look at the traveling wave equation, and we're going to think about this as a singularly perturbed system of equations, right? So you get this kind of traveling wave equation. You rewrite it as a system in slow-fast form. Note that kind of there's this, effectively, there's a v double prime term in the first equation, right? So it's not kind of just the standard reduction to a slow-fast form, but you have to kind of think a little bit about kind of what the right variables are for the slow-fast reduction. But you get basically this system of equations in slow-fast form, okay? Now you want to kind of apply kind of a singular perturbation type reduction. So you set delta is equal to 0. What that does is it reduces this system of equations to a system of 2 ODEs coupled to a system of 2 algebraic equations, okay? So what you think is kind of in the limit, you should lie near basically solution sets of these algebraic equations. And so when delta is equal to 0, you obtain kind of this slow manifold, which ends up being normally hyperbolic, okay? So when you reduce or when you restrict yourselves to being on that slow manifold, so you plug in basically the value of the slow manifold in for h and z in the first two equations, you get a reduced equation. This ends up being exactly kind of the reduced equation that you got in that very formal thing we did at the beginning of the talk, where you just set u equal to v and plug that into the first equation, okay? This is a scalar equation. You can find kind of pushed and pulled fronts in this. So if d is bigger than a half, you have pulled fronts. If d is less than a half, you have pushed fronts. We know everything about kind of their stability and what kind of spaces they're stable in, and so good. So we understand everything in the reduced limit. And now the question is basically, does this kind of survive when we look at it for delta small? Okay. So what you do here is Scheel gives you basically the tools by which to do this, right? So when delta is equal to 0, you have this normally hyperbolic slow manifold. It will perturb smoothly in delta. So that's kind of Scheel's main result, right? Is that for delta sufficiently small, this manifold perturbs smoothly into a new manifold M delta. This is invariant under the flow, and it contains all of your kind of bounded solutions. Moreover, you can kind of write this as a graph with expansions in delta, okay? So that is kind of our reduction. Okay, so existence-wise, like everything is kind of good, right? So we have this kind of normally hyperbolic manifold that when delta is equal to 0 contains this front solution. It perturbs to a normally hyperbolic manifold when delta is non-zero, and it again kind of contains this front solution. Okay, so we basically get this kind of existence in the small delta regime from this Scheel type result. Now, the next thing is you want to talk about stability, okay? And so the stability problem, this looks very complicated, right? But really what you're doing is you're linearizing about the front, you're computing kind of your stability, you're looking at your stability problem, and you're writing out the combined existence and stability problem as this big system of 8 ODEs, okay? So you have your existence problem here, you have your stability problem here. They're both singularly perturbed systems of equations, okay? So you can apply kind of a Scheel type reduction to these as well, okay? And so what you get is that, again, you kind of recover this slow manifold for the existence problem, and you get now a slow manifold for the stability problem as well, okay? The relevant fact here, right, is that the slow manifold for the stability problem remains linear, okay? The system's linear to begin with, so it's linear in the variables u tilde and w tilde. And it contains all of your bounded solutions, right? So you don't have to worry about any sort of eigenfunctions transverse to this manifold. You only have to worry about eigenfunctions within the manifold. And so what you do is you have this kind of existence problem, which I just talked about. And then the stability problem, again, kind of reduces down to a scalar problem, which you can then kind of analyze using these kind of regular perturbation results that I talked about earlier. Okay, so I went very quickly there, so I apologize. I like to finish talks on time, and I realized I was just a little bit behind, and so I wanted to kind of get there on time. So I just want to kind of illustrate again kind of like the main ideas, okay? So we have these regular perturbation results that tell us that, when we make small perturbations to a scalar reaction-diffusion equation, we can get the persistence of either pulled or pushed fronts, and they remain stable. They maintain the same stability properties that they have in the reduced problem. Okay, the the way that we kind of then do this is that we apply finish L to the combined existence and stability problem to kind of, so that when we kind of look at the full system in the case where delta is small but non-zero, we have basically a reduction from these finish L reduction theorems onto this kind of now manifold that is lower dimensional but close to the manifold in the singular limit. Okay. Okay. So the main result, right, is that you can kind of perturb these pulled and pushed fronts that you obtain in the singular limit together with this kind of push to pull transition. And again, what I said is it's kind of fun in this case, right, because you can compute a lot of things explicitly, so you can actually kind of come up with explicit but kind of ugly corrections to the speed in the pushed case. You can come up with an explicit but kind of ugly correction to the location of this push-pull transition. And I'll say just kind of in closing, right, I mean, this is kind of asymptotic stuff. So you expect kind of when delta is sufficiently small that this should work. The hope is always that it actually pertains to larger values of delta, right? So the first thing you might do is you might say, okay, well, where is this transition as a function of delta for larger values of delta, and compare it with the estimate that you get from the case with small delta. And it's really remarkable in this case that actually kind of the linear prediction works really unreasonably well as a prediction for where this transition is, all the way up to kind of around delta squared is about a half, okay? We did a lot of look at this, and it's not actually linear. It appears to be genuinely non-linear, but with a very small kind of second order deviation. So that's kind of the talk. I apologize a little bit for my timing. I spent a little bit more on the background and a little bit less on the research aspects, but I hope you came away from this talk, if you didn't know already, with an understanding of kind of the difference between pushed and pulled fronts and some of the kind of things that you have to deal with when you're talking about front propagation into unstable states. And so I'll just end here with a couple references, and I'd be happy to answer any questions if there are some.
Okay, great. Thank you, Matt. That was a great talk. Thank everybody. Please thank our speaker. And of course, if you have questions, please feel free to chime in.
Well, I'll wait. Does anybody have questions? Because I have a few questions.
I also have a few questions, and I have to run for another seminar at 4.
Then you go first. Go
ahead. Thanks. So I really appreciate that you took the time to do the background, because I could follow along and feel like I was understanding the research component a little bit too. But I was wondering, so when you're talking about the selection of pulled fronts in like the basic scalar reaction diffusion, I guess I was wondering, like, what is it that's giving the selection, and what is the significance of losing that transitional symmetry in the unstable case?
The translational symmetry.
I guess in the case of when you're looking at like C greater than 2, C equal to 2, the criticality there.
Okay, yeah. So yeah, that's a really great question. It's a little bit hard to understand, right? Why the speed C equal to 2 front is the front that you see, right? So in the Fisher KPP case, you have actually kind of a comparison principle. So probably the easiest way to understand why compactly supported initial conditions go to speed 2 fronts in Fisher KPP is that you can construct sub and super solutions, and it's not so hard to construct a super solution for any speed C bigger than 2, right? Which kind of implies that compactly supported initial conditions can't move faster than that. Okay, so that's kind of the easiest way to see it, which is admittedly nothing that I talked about today, right? But that's kind of the idea. Now there's Montie and Arnd have a nice paper where they basically show that the spectral assumptions that I kind of laid out are sufficient for a large class of elliptic PDEs to kind of select the front that has those kind of marginal stability characteristics, right? So that's another way that's a more complicated way to see kind of why you get that front.
Okay. And then you were saying like we have an understanding of the stability of the selected front by like knowing that the absolute spectrum is on R minus, but we don't have that isolated eigenvalue at 0. So what
Right.
is like, what does that mean for the pulled front
Yeah, so in terms of stability, that's
or
a great
push?
question. And yeah, so what you end up seeing is that because there's no kind of embedded translational eigenfunction at the edge of the essential spectrum, you see basically faster than heat kernel type decay, right? So the decay rate that you see there ends up being like something like T to the 3/2 type decay. And so that's something that Thierry Gallet discovered, I think, back in the 90s, and there's been kind of work on that since then. Does that answer your question?
Yeah, enough, I think. I'm
Okay.
not sure I have the background to understand that, but thank you.
Yeah.
Okay, well, Matt, a few questions. So, I mean, that was a great talk, man. I appreciate that. And I really like the fast load decompositions that you did and relate them to the Fenchel theory. So basically, your talk for the Keller-Segel, basically you get existence and you also get some stability. I mean, you get stability, but I'm trying to relate that to your first half, right? So you talked
Yep.
about this translational eigenvalue, right? So did you?
Eigenfunction, yeah, or eigenvalue. Yeah, go ahead.
The eigenfunction. But did you compute that explicitly for this particular thing for the Keller-Segel?
So okay, so you'll the derivative of the wave, right, is
Yep.
always a solution to the eigenvalue problem with lambda equal to 0. Okay.
Right.
But the thing that makes it a little subtle here is that you want to look at these problems in exponentially weighted spaces, and depending on which problem or which weight you're looking at, that translational eigenfunction might be in the space or it might not be in the space.
Okay. So can you discuss a little bit more about this exponentially weighted space? Like, how does that come into factor here?
Yeah. Go back. Yeah, so like it comes up really in maybe I should do it here. So in the stability, right? So like I said before, right? I mean, if you don't use an exponential weight, these fronts are always unstable, right? Because they're fronts that are propagating into an unstable state. So kind of, by definition, if you make a perturbation ahead of the front interface, it's going to grow, right?
Right.
So the exponential weight serves to basically kind of localize the set of possible initial conditions to be near the front interface in a certain sense, right? So you're basically saying, okay, my perturbation has to be small after I multiply it by this exponentially growing weight, right?
Gotcha.
And the effect of that, if you look at it in an exponentially weighted space, is it moves this essential spectrum, right? So this essential spectrum here really is an indicative of this instability. And so as you change the exponential weight that you're working on, this essential spectrum moves around. In the pulled case, right, you can push it you can move it all the way to the negative real axis. In the pushed case, you can actually stabilize the essential spectrum, okay? And what's important is for a push front, you have to do it in such a way that the translational eigenfunction remains in the space.
No,
Okay.
I got it. Yes.
Okay.
I mean, so yeah, I did get that. So what I'm saying is like, how did you apply this particular like method? I didn't see it explicitly into the Keller-Segel model.
Okay, yeah. So in the Keller-Segel case, this is all kind of stuff that you have to kind of check beforehand, right? So you have this kind of the essential spectrum all comes from the linearization about the unstable state, right? And so you have to, I guess, so yeah, I mean, this is something that you have to kind of check before you start analyzing the problem. But I'm trying to think. I don't remember exactly the specific details of this, right? But
Well, I could always read the paper and see it's in there,
yeah,
right?
no, my recollection is this is something that you can just kind of do explicitly, and you can see kind of that as you work in a different space, you can kind of stabilize or at least marginally stabilize the essential spectrum.
Okay, okay.
I mean, you're right, though. It's a system, right? So it's more complicated, but
That's right. That's I was curious about that. That's all.
yeah. Yeah. Good question.
Any other questions for Matt? Okay, if not, thank you again, Matt. Great talk, and I thought actually the cartoons looked great, so.
Thank you very much. Thank you for having me and yeah, listening to a non-climate talk this week. So
These equations are everywhere anyway, so it's all related.